Hello. Today I will be talking about reactions of alcohols. There are a number of different reactions of alcohols, and we will be covering quite a few of them in this chapter. So in order to make it a little bit simpler, I've broken it down into four main types of reactions. So let's talk about the four main types first, and then we'll talk about the individual reactions under each type. So the first type will be where we replace the whole OH group of an alcohol with something else. In this chapter, really the only thing we're going to be replacing the OH group with is a halogen. So notice that the OH group of the alcohol can be replaced with a halogen, and that can be bromine, chlorine, or fluorine. We'll learn several different ways of doing that. Second major type will be where we don't replace the whole OH group, we just replace the hydrogen of the OH group. And there are two things that we can replace the hydrogen with. One is another alkyl group, in which case we get ethers. And the other is we can replace the hydrogen with this fancy group, S double bond O, and then another carbon group. That's called a sulfonyl group. And so we make sulfonates, sometimes called sulfonyl esters. And you'll learn more about those in another video, but we'll talk about how you make these today. Notice that in both of these reactions I've put a prime on the other R group to indicate that they may or may not be the same as the R group of the alcohol. So we're actually dealing with two different carbon groups in both of these molecules. So that's the second major type, and we'll talk about both of those reactions in a minute. The third major type is an elimination reaction, where we don't replace anything. Instead, we get rid of the OH and we get rid of a hydrogen next door and put in a double bond. So that's a familiar type of reaction called elimination. Specifically, the elimination reaction from alcohols is called dehydration, because what is it we're taking off? An OH, a hydrogen, that makes water, and so we're dehydrating it or getting rid of water. The product is always alkenes, so we'll talk about that reaction a little bit more here in a minute. And then finally, the fourth major type is called oxidation, and we'll have to review a little bit about redox reactions in general, which we will do in class, but the oxidation reactions of alcohols, essentially what we're going to be doing is taking C single bond O of an alcohol and making it into a C double bond O by removing hydrogen and removing actually another hydrogen from the carbon next door, putting in a double bond O, and in some cases not only putting in a double bond O, but also putting in another OH group, not the same as the original OH group. And so the products of oxidation are aldehydes and or ketones and or carboxylic acids, and we'll learn more specifically about which of those you get in certain cases when we get to that here in a minute. So let's start with the first major type. That's replacing the OH group with a halogen. There are two ways of doing that. There's an old-fashioned way and a more modern way. The old-fashioned way of replacing an OH group with a halogen is simply to use HCl, HBr, or HI, hydrochloric acid, hydrobromic acid, or hydriodic acid. And if you react an alcohol with hydrochloric acid, you get an alkyl chloride. And notice that the hydrogen from the alkyl chloride and the OH from the alcohol go together to form water. So we're making an alkyl chloride, or if we use HBr instead of HCl, we're making an alkyl bromide, or if we use HI instead of HCl, we're making an alkyl iodide. So it's basically the same reaction in all three cases. You could just put the X in instead of chlorine, bromine, or iodine, and generically you'd be making RX, which is an alkyl halide. So it's a pretty simple reaction. It's an old-fashioned reaction and one with a pretty simple mechanism. So let's learn the mechanism of this reaction. Actually, as you might guess, there's two mechanisms, an SN1 type and an SN2 type. We'll talk about why they're called SN1 type and SN2 type instead of just SN1 and SN2. The reaction will go by an SN2 type mechanism if the alcohol is primary. So think about this alcohol as being, say, ethyl alcohol or N-propyl alcohol, and then it's going to be what we're going to refer to as an SN2 type mechanism. So what does that involve? Well, in the first step, the alcohol reacts with HCl, HBr, or HI, which of course is a strong acid, strong enough to protonate the oxygen, and so you simply transfer an H plus onto the oxygen, gives you this protonated alcohol with a positive charge on oxygen, and that's a familiar intermediate you've seen before in other mechanisms. Then, in the second step, the protonated alcohol serves as a leaving group. The halide that was formed in the first step is the nucleophile. The nucleophile comes in from the back, attacks the R group, and pushes out the water. And so you get your alkyl halide, and you get the water which was the leaving group. Now let's look at that second step here in more detail. Notice that here comes the halide in on the back and pushes out the water from the front, and you get your R group with a halogen now attached on the back and the water having left from the front. So it's backside attack. That's typical SN2. So why do we call it SN2 type and not SN2? Well, let's go back to this mechanism and notice that it's really the second step that's the SN2 reaction or mechanism. But before that can happen, we have to do a preliminary step in which we first protonate the OH group. You can't do it directly on an alcohol because then the leaving group would be hydroxide, and hydroxide is a terrible leaving group. It doesn't want to leave at all. If you protonate first, then the leaving group is water, and that's a fine leaving group. So to summarize, you have to protonate first, and then you do the SN2 mechanism. And so that's why we call it SN2 type, not SN2 directly. Now, if the alcohol is a secondary or tertiary alcohol, so this alcohol might be isopropyl or T-butyl alcohol, the first step is the same. You react the alcohol with the hydrohalic acid, HCl, HBr, or HI. It protonates the OH, and you get this protonated alcohol. So the first step is exactly the same as the first step was in the previous mechanism with primary alcohols. But now what happens is this protonated alcohol, instead of being attacked directly by the halide, loses its water first to form a carbocation. Notice in the previous mechanism we didn't have any carbocations. So you form a carbocation here, and then once the carbocation is formed in a third step, the halide can attack the carbocation and form your alkyl halide. So these two steps, leaving of the water to form a carbocation and then the attack on the carbocation by the nucleophile halide, is essentially an SN1 mechanism. But again, we call it SN1 type because there's a preliminary step in which you have to protonate the OH first. Right? Now, one other thing to notice about the SN1 type mechanism is, since this is a carbocation, it can do other things that carbocations do, for example, rearrange. So if this were a secondary carbocation and there were a tertiary available by simply shifting a hydrogen or a methyl group, then that's going to happen, and that would constitute the third step, and then this one becomes the fourth step in the mechanism. So don't forget, if it's secondary and it can rearrange to tertiary, it will do so, and it will then become a four-step mechanism instead of a three-step mechanism. Now, that's the old-fashioned way of making alkyl halides from alcohols. Simply react them with a HCl, HBr, or HI. There are a couple of newer reagents that have been developed that do the job much better. They don't involve any rearrangements. There's no problem with eliminations. They happen quickly and at room temperature and give very few byproducts. So let's learn what those are. Really, it's two different reactions, but we're considering them together as one reaction because they essentially do the same thing. First, you can take an alcohol and react it with this compound SOCl2. That's called thionyl chloride, THIONYL, thionyl chloride. And you might want to try drawing a Lewis dot structure for this just to see what it would look like. I'll go ahead and tell you the skeleton. The sulfur is double bonded to an oxygen, and then the two chlorines are each bonded separately to the sulfur. So it's chlorine, sulfur, chlorine with a double bond O on the sulfur. That's called thionyl chloride. And when you react it with an alcohol, very quickly, easily at room temperature with no problems, the OH group gets replaced with a chlorine, so you make an alkyl chloride. You also get sulfur dioxide as a byproduct. That's a gas and disappears out of the reaction mixture. And you also get HCl, which, because there's no water here, is not hydrochloric acid. That's just the gas, hydrogen chloride, and it disappears from the reaction mixture as well because it's a gas. So you really just end up with your alkyl halide in good yield very quickly. So this is a good way of making alkyl chlorides if you want to from alcohols. If you want to make an alkyl bromide instead, it's not quite so simple because there is no SO-Br2. It would be nice if there were, but there's not. And so we use this reagent phosphorus tribromide. You could draw a Lewis dot structure for that as well. It's very simple, just a phosphorus with three bromines and a lone pair on the phosphorus. In any case, this reaction does essentially the same thing. It replaces an OH group with a bromine, and so you get an alkyl bromide in good yield. Now notice that the byproduct here is, I've written it as P with three hydroxides on it. It could be written as H3PO3, which would be called phosphorus acid. It doesn't disappear out of the reaction mixture. It needs to be separated out. So it's not quite as convenient as this reaction up here in which all the byproducts just disappear. But it's still a good way of making an alkyl bromide if that's what you want to do. Now the balance equation is a little complicated because all three of these bromines get used to replace OH groups, which means you need three equivalents of the alcohol to start with, and you get 3 equivalents of the alkyl halide. But that's just balancing the equation. Typically this would be written as ROH with PBr3 over the arrow, and then RBr as the product of the reaction. Now these reactions are both a little bit complicated in terms of their mechanism, so we won't be learning mechanisms of either of those. And so just to summarize, there's 5 reactions in which you can replace an OH with a halogen. You can use HCl, you can use HBr, you can use HI, you can use thionyl chloride, or you can use phosphorus tribromide. Now, the second major type of reactions of alcohol is actually one that we learned about in the earlier in this chapter 10. It's really a 2-step, one-pot synthesis, and the first step is that you react the alcohol with sodium. That's sodium metal, not sodium hydroxide or any other sodium compound, but the element sodium, and that produces a sodium alkoxide. The hydrogen gets doubled up essentially and turns into H2. And to keep the equation balanced, we need to put a 1/2 in front of that, but that's a gas and it disappears out of the reaction mixture, so you get this sodium alkoxide. Again, that's a reaction you learned earlier. You then take that sodium alkoxide and right in the same flask. You don't never actually isolate it. You just use it directly. You add into it an alkyl halide, and the alkyl halide then does an SN2 reaction, and the alkoxide comes in, attacks the back of this alkyl group, and pushes out the halide, and so you get X-, which goes with the sodium and produces sodium chloride, sodium bromide, or sodium iodide. That crystallizes out and pretty much gets thrown away, and the product then is this ether. And this step really constitutes the Williamson ether synthesis. It's an alkoxide plus an alkyl halide goes to an ether. Now, one thing to remember about it is that it really only works if the alkyl group, this R' that I've indicated here, is a methyl group or primary. If this is a secondary alkyl halide, or especially if it's a tertiary alkyl halide, you get elimination, because remember, alkoxides are strong bases. Strong bases with secondary or tertiary alkyl halides give elimination, so you really don't get the ether, you get an alkene instead. So there's that limitation that this really needs to be methyl or primary, but if it is, then this can be a useful way of making ethers. The second major reaction under ways of replacing a hydrogen with something else involves this fairly complicated looking molecule. Looks kind of like thionyl chloride that we saw a few minutes ago, but it's not. It's nothing like it. This isn't actually a carbon group, so this is an organic molecule. It has a carbon group with a sulfur, 2 double bond O's, and a chlorine directly attached to the sulfur. This is called a sulfonyl chloride, and we'll be learning more about them in a separate video. But essentially what happens is the oxygen from the alcohol replaces the chlorine, and so you get this R'(O) attached onto the sulfur. So the R'(O) attaches onto the sulfur, the hydrogen from here and the chlorine from here go away and produce HCl, which bubbles out of the reaction mixture, and you end up with this kind of compound, which is variously called a sulfonyl ester, or sometimes called just a sulfonate. And we will be learning about reactions of them in a separate video, but you need to be able to write this reaction down. Next is our third major type of reactions of alcohols, and that is dehydration, which is an elimination reaction. And it's fairly simple. You just take an alcohol, add concentrated sulfuric acid to it, and generally you're going to heat it, and the product is going to be an alkene. Of course, water is a byproduct of this reaction. Looks kind of like dehydrohalogenation that you learned in an earlier chapter, where you have a halogen on here and take off a hydrogen next door and put it in a double bond. But that, you remember, uses a strong base as the reagent. This is different. This is an alcohol, not an alkyl halide, and it uses a strong acid as the essentially a catalyst in this reaction. Now let's learn the mechanism of this reaction. The first step is that the sulfuric acid protonates the OH of the alcohol to produce a protonated alcohol. Again, that's the same as the first step in the SN1 and SN2 type mechanisms we saw a few minutes ago. So you're simply protonating the OH, put a second hydrogen on there and a positive charge on the oxygen. The conjugate base of the strong acid then is HSO4-, so that's hanging around as a counterion. In the second step, this alcohol loses water, and so you form a carbocation. Now the interesting thing about this is that it happens even if this is a primary alcohol. So even if this is a primary carbocation, it still forms in this reaction. It's a little bit unusual and not what you would expect, but it makes it easier in some ways because there's only one mechanism. It's an E1 type. There is no E2 type elimination for dehydration. In any case, that carbocation may very well rearrange, especially if it is primary, but even if it's secondary and it has a possibility of becoming tertiary, it will rearrange. I haven't shown that as a step here, but that would be a third step if there was a rearrangement. And then what is shown as a third step here would become the fourth step. And essentially what happens then is that the carbocation loses an H plus from next door and becomes an alkene. So it's a three-step mechanism unless there's a rearrangement, in which case it becomes a four-step mechanism. Protonate, lose water, and then lose H plus. And the thing that picks up the H plus, at least to keep things balanced, is the HSO4 minus that was formed in the first step, and that reproduces the H2SO4, which then goes back into the mixture, and that's why the H2SO4 is simply a catalyst, because it's used up in the first step and it's formed again in the third step. So that's the mechanism of dehydration. Now the fourth, that should be a 4, not a 3 there. The fourth major type of reaction is oxidation, and this gets a little bit complicated. So there's 4 different ways that you can oxidize alcohols. The first one happens if you have a primary alcohol. So I've written the alcohol here with a CH2 in here just to emphasize that this is dealing with primary alcohols. Then we use a reagent called Jones reagent, and you can memorize it as simply Jones reagent. But let me talk a little bit more about what that is. Jones reagent is really chromic acid, which is H2CrO4, and it's formed by, and notice that the oxidation number of the chromium here is +6. We can go back and think about why the oxidation number is +6, but I'll let you think about that for the moment on your own. In any case, any kind of +6 chromium reagent, if it's dissolved in acid, becomes chromic acid, and essentially is then called Jones reagent. So you can do this by putting chromium 6 oxide or potassium chromate or sodium chromate or potassium dichromate or sodium dichromate in sulfuric acid or in acetic acid. Those are all different types of reagents that all basically are called Jones reagent, and they will cause a primary alcohol to become an aldehyde. It happens because it's taking off a hydrogen from the oxygen, and it's taking off one of the 2 hydrogens from next door and putting in a double bond. That constitutes an oxidation. So if you figure out the oxidation number of the carbon in this molecule and the oxidation number of the carbon in this molecule, you will see that it has a bigger positive number. Again, we'll talk about that in class, but this is essentially an oxidation. Now notice that in this equation I have written the aldehyde in brackets, because the fact is aldehydes themselves are very susceptible to further oxidation. By inserting an oxygen into this carbon-hydrogen bond of the aldehyde, it becomes a carboxylic acid, and that's essentially what you get. So if you start with a primary alcohol and use Jones reagent, you don't actually see the aldehyde. Instead, you go all the way to a carboxylic acid. So what you need to memorize is primary alcohols with Jones reagent give carboxylic acids. But what if we wanted to stop at an aldehyde? What if we wanted the aldehyde by oxidizing a primary alcohol? Well, there has been a reagent developed. It's a more complicated reagent than Jones reagent. It's called PCC. PCC stands for pyridinium chlorochromate, which I've drawn the structure here for you. So, oxidation of primary alcohols with PCC gives aldehydes. So let's review. If you oxidize a primary alcohol with chromic acid, otherwise known as Jones reagent, you get carboxylic acids. If you oxidize primary alcohols with PCC, you get aldehydes. Now, what if your alcohol is a secondary alcohol? I've drawn an example of a secondary alcohol here. In other words, just basically a carbon with an OH on it and 2 carbon groups, so it's secondary. Use much simpler reaction. Using either Jones reagent or PCC gives you a ketone, and there's no alternative. That's the only thing you can get because you just have 1 hydrogen on the carbon and 1 OH group. So you can only form a double bond O with the 2 carbon groups left over. And finally, what if you have a tertiary alcohol and you try to use Jones reagent or PCC? The answer is you get no reaction, because notice that if you try to put a double bond between the carbon and the oxygen, there's no hydrogen you can take off. That would be 5 bonds of carbon, and you can't do that. So tertiaries give no reaction. So again, primaries with Jones reagent give carboxylic acids. Primaries with PCC give aldehydes. Secondaries with either Jones or PCC give ketones, and tertiaries don't react at all. That's the end of the talk for today. Thank you.